Thank you for joining us and welcome to the 7th webinar in our series on integrating dynamic modeling and simulations into your courses. In this series, we feature experienced professors from various fields who have shared their insights on incorporating dynamic modeling and simulation into their coursework. Our goal is to provide you with a starting point and direction to begin implementing these techniques into your own teachings. Today's webinar, presented by Dr. Rob Alexander, will focus on using dynamic modeling in environmental courses. But before we begin, let's briefly review some webinar mechanics. On the bottom bar, you will see some audio setup. If you're having trouble hearing us, please look there to make sure you can hear this. And on the top bar, you will see the box with the question sign in it. That is where you will be writing in your questions. We will have time for a Q&A at the end of this, so please feel free to write them in. Now, allow me to introduce our presenter. Dr. Rob Alexander recently retired from Kenyon's College, where he was professor of economics and environmental studies. Having dual citizenship in the US and New Zealand, Rob has taught in both countries and has taught water economics at the United Nations Environmental Program. He has worked on conservation issues at the Kruger National Park and as with the State Forest Administration of China on the economics of tiger conservation. Rob, we would like to say congratulations on your recent retirement, and we are thrilled to have you with us today.
Thank you, Hillary. Good afternoon, everyone. I'd like to thank Hillary and IC Systems for inviting me to speak today about how I use Stella in my teaching. Although we use Stella in several courses today, I'd like to talk about just one project in the course we call Applied Environmental Analysis. The course is designed for sophomore students who've decided they want to major with us. Many students interested in environmental studies do have a science and math background, but most don't. And this course is our way of preparing students to use the types of quantitative tools that we expect them to see in their advanced courses or when working with faculty on research. Stella is one of 3 modeling systems we use in the course, but it is in particular central in that one of our curricular goals for the program as a whole is for students to learn to think in systems. And Stella is central to helping our students understand what we mean by that. In the particular project I'm going to talk about today, the models we build are based on a case study by Andrew Ford in his book, Modeling the Environment. This is an excellent book that would serve as a great text for an entire course in environmental dynamical modeling. I love this particular case study from the book because it's so comprehensive and it addresses the goals I had set for the project even before choosing this particular scenario. So the base models we're going to look at today and that we use in class are Andrew's. And then from there, we expand into additional policy options and other variations on the models. I have 4 learning goals for the project. The first is to give students an introduction to building models in Stella. Many of our students have used it in an earlier course just to diagram relationships between elements of systems. But for most of the students, this is their first working dynamical model. The second is to help students think about a problem set of, or a problem as a set of interacting systems. And this exercise requires them to consider hydrology, ecosystems, economics, politics, our legal system, and all of these bear on the policy recommendation I'm going to ask them to make at the end of the exercise. The third is that I want them to develop good habits in modeling. In this project, and honestly throughout the whole course, I emphasize principles such as modeling incrementally, documenting your models, using units explicitly, validating models, interpreting results. Fourth, I want them to understand that despite their passion to fix our world's environmental problems, operating in a policy context is a slow, uncertain, and frustrating process. This case study is perfect for that. They see that their models tell them what the characteristics of a potentially successful policy would be, but then they see that the policy that was ultimately adopted in the real world couldn't possibly have achieved its stated goals. Finally, as an ongoing issue for 80 years, we can see the span of time acting on society and environment. We can step into this issue halfway through, model our policies, and then still see what happened afterward. In this case, we're going to see that we've made relatively little progress toward our stated goals in the 40 years since this policy was enacted. And sadly, the students need to know that's another reality of environmental policy work. So that's what I'm trying to do with them. That's what I'm trying to achieve. Let's jump into the project and take a look at Mono Lake. Mono Lake is an ancient saline lake. See, it's right up here on your map. And it is in the eastern Sierra Nevada near the town of Lee Vining in California. It's estimated to be over 760,000 years old. It's one of the oldest continuing existing lakes in North America. Part of its longevity is due to its closed basin geography. Water flows in from surrounding streams, but it has no real outlets, and so it only really leaves through evaporation. This has led to the accumulation, of course, of salts and minerals over millennia, giving the lake its distinctive chemistry and its high salinity. The lake's landscape is strikingly otherworldly. Tufa towers rise dramatically from the lake bed and the shoreline. These are limestone formations created by the interaction of calcium-rich spring water and the lake's existing carbonate-rich water. So volcanic islands, including Neged and Poha in the left picture, punctuate the lake's surface. And then surrounding the lake, although these pictures look quite moist and green, but surrounding the lake is this high desert ecosystem with really stark contrast between the arid land around it and the expansive water that is the lake itself. So the lake supports a unique and highly productive food web. Despite its salinity, it teems with life. Microscopic algae thrive in its waters, feeding vast populations of brine shrimp and alkali flies. These invertebrates in turn attract millions of migratory birds, including California gulls, phalaropes, grebes. The lake is a critical stopover and nesting site on the Pacific Flyway, making it an ecological oasis in a pretty harsh environment. So this is a pretty unique place, and it's not surprising then that this becomes a focus of some environmental consideration. And the story of the decline of the lake starts back in the 20th century with the growth of Los Angeles. As the population surged from 100,000 in 1900 to over 1 million by 1930, Los Angeles sought new sources of waters beyond the existing Los Angeles River. And the city completed the Owens Valley Aqueduct, so this part along here, first in 1913, and by 1941, it extended its reach then up to the Mono Basin up here. And so that year, Los Angeles began diverting water from, not from the lake, of course, itself, since it's a saline lake, but from the streams that feed the lake. And they redirect that into the Owens River system, and eventually it gets transported 400 miles to Los Angeles. The diversions are largely gravity fed and even generate some hydroelectric power along the way. By the 1970s, the average annual diversions from the Mono Basin reached approximately 100,000 acre feet, which is roughly 2/3 of the lake's natural inflows. The impact of these diversions was dramatic and measurable. Right? You can see on the graph of the lake's elevations here what happened over time. And so the lake's level between 1941 and 1981 dropped by 45 feet, from 6,417 feet above sea level to just 6,372. Its volume was cut nearly in half, and its surface area shrank by 10,000 acres. As water evaporated but was not replenished, salinity levels doubled from about 55 grams per liter to over 100 grams per liter. This increase in salinity threatened the lake's algae, which in turn jeopardized the brine shrimp and the alkali flies. And the ecological ripple effects were severe. As the lake receded, a land bridge formed to Negat Island, the smaller of the two islands in the previous picture, exposing nesting gulls to predators. Dust storms intensified because of the exposed lake bed sediments, and the system started to approach critical thresholds for ecosystem collapse. By the early 1980s, scientists and environmental advocates warned that continued diversions could lead to the complete collapse of the lake's food web and the loss of its role as a vital bird habitat and migratory stopover. So, concerned by the lake's decline, it was actually a group of environmental science students who formed the Mono Lake Committee in 1978. And their grassroots advocacy drew national attention. And in 1979, the National Audubon Society took over this cause, and they filed suit against the city of Los Angeles. The case eventually reached the California Supreme Court, which issued a landmark ruling in 1983. The court held that the public trust doctrine, which requires the state to protect natural resources for public use, does apply to Mono Lake, and that Los Angeles's water rights really have to be reconsidered in light of the ecological harm it was causing. So following the ruling, the State Water Resources Control Board took on a comprehensive review of diversion policies. It was essentially set the task by the court to find some compromise between the different competing needs of the lake. And it considered several alternatives, ranging from unrestricted diversions to a complete halt. Modeling studies projected that without restrictions, the lake would continue to decline and would stabilize if diversions continued at the 100,000 acre feet level at around 6,335 feet. So, and which is far, far below the threshold at which we would expect ecological collapse. Conversely, stopping all diversions could allow the state to recover, the lake to recover to more than 6,400 feet over about a century. In 1994, the board issued its decision. Diversions would be limited to allow the lake to rebuild a target elevation of 6,392 feet, and that's the level it stood at in 1963. This compromise was aimed to balance Los Angeles' needs with ecological preservation. There's a plaque of the lake's boardwalk now, which marks this target elevation. And however, as subsequent modeling and real world data have shown, progress toward that goal has been pretty slow. And the lake remains well below the target to this day. So for this exercise, we step into this scenario in 1990. So the Water Resources Control Board has set some guidelines. We're in the process of negotiating between Los Angeles and concerned parties about the environmental issues. And our role in the exercise is to model the hydrology of the lake and to predict how various policy proposals will impact the long-term health of the lake and its ecosystem. After building the model, the students will review several policy proposals that were actually suggested at the time, and then they will develop their own recommendation for diversion rules, and they'll submit that to me in a report that is ostensibly to the Water Resources Control Board. Before doing this exercise, students really have only been briefly introduced to Stella, having most of them having run through a population model tutorial in the previous class, so they know how to use the model interface, and most of them having seen the model in a previous course where they just looked at the relationships between stocks and flows. But given that this is the first time most of the students will have built a model like this and run a model like this. I approach the exercise by alternating models with the students. Right? So we build a model together in class, and then they build a model, an extension of that model as homework. Then we come back, build another model in class, they go back, build another model. And in that way, we not only reinforce the concept of modeling incrementally, but we also make sure, or hopefully make sure, that we don't completely overwhelm the students by asking them to make too large of a conceptual leap with this. And so this has worked really well for me over time. So in the end, by the way, I do ask the students to come up with their own policy. We're going to look at some policies that were proposed. I'm personally not particularly impressed with any of those policies per se in the form that they were proposed. And so I asked the students to come back, and each of them to simply give me their own policy, and also then to create a model that demonstrates how that policy would work over time. So let's step through it. Let's look at the models themselves. We build model 1 together, and while I know what it will look like, and that it will look like what you see on your screen, I start with a blank screen, and I just ask them to imagine the types of stocks and flows that would be needed, right, to estimate the volume of water in any lake over time. And we talk through it, and of course through guiding them with what's needed and not needed here, since I know where we're going, we end up with this model. And this particular model results in 3 inflows and 2 outflows, really 2 principal inflows. Precipitation, which in this case means precipitation directly onto the lake, and then flow into the lake from local streams, which is called Sierra gauged runoff. There's another small other in, which are relatively quite small relative to the other 2 inflows. And similarly, the other out is very, very small next to evaporation, which is the main outflow into this model. And so as we do this, the students, so we look at this, the students are building it with me, and they need information to make this work. So they have, over the course of the assignment, 3 data sheets. So this is the first of the data sheets, and this provides them with what they need in terms of actual numbers to go into the different model elements. And it also, gives them some guidance as to how to do things, what to do, and what their assignments are. This that you see on your screen now is just the first half of the data sheet 1. We'll look at the other half in a minute. The other thing we discuss here for model 1 is this concept of a reference mode. And so we talk through why it is that we expect the lake to reach some kind of equilibrium, even when we're taking out all of this water every year. There is still water flowing in every year. So of course, the lake isn't going to reach 0 volume, but it is going to reach an equilibrium somewhere. And so the first task I'm setting for them is just to see, do we have a model that meets the reference mode? And of course, the same slide you saw a minute ago. Of course, no, we don't, right? This is just a linear decline to 0 after 40 years. So we know that this isn't doing, what we want it to do. And so it makes sense, of course, right? If you're looking at this model and you're looking at the data that was in there, you'd be thinking, well, of course it's linear. There's nothing in that model that's not linear. And that's true. And so that's part of the class exercise. And right, that's what we want to do is work together to figure out, well, what could be wrong here? And so during conversation, we look at the problem. I ask them to examine the different parts of the model. And we always, of course, arrive at the problem. And the problem here is that the fixed surface area assumes the lake is effectively shaped like a cylinder, right? So it's the lake volume declines, the surface area stays the same, evaporation stays the same, and so there's no nonlinear component to allow it to settle out into an equilibrium. And so as we do this then and recognize the lake is shaped more like a bowl than a cylinder, then this is going to be their first task. Their first task is going to be to make this model look like the reference node. And so when we do that by giving them some information that is the actual information relative to the lake. So the lake had a lot of geologic surveys done, so we have really good data on the lake. And so we have this relationship between the volume of water in the lake and the surface area of the lake. And so in that way, we can build that into the model. And we're going to build that into the model using a graphical function for a surface area. So instead of this constant, we're going to allow that to change with the volume of water in the lake. We also talked to them about how to do that and go through how to make a graphical function. So really for them, this first step is pretty small because they understand what they're trying to do. They have the numbers. They've learned how to enter a graphical function, and they just need to go away and do it. And I do this as a small test simply because my classes are Tuesdays and Thursdays. We start this thing on a Tuesday. They only have till Thursday. I want them to only have a small assignment to do there so that their first step is one that they can succeed with. And so they do, right? So they go away, they do this. Over on the right here is the graphical function area, and you can see the values from that table that I just showed you in here. And so as they come in and they run this again, they do in fact see they see the reference mode. So we've at least got the right shape of things going on here. Now, we do one other thing, or we're about to do one other thing as we go in here. So we've come back. This is a Thursday. They built this model that you're looking at, and we're going to build model 3 here. And so as we build model 3, what we're going to basically add is really the important thing that we're adding is elevation to the model. And this isn't, of course, changing the model. This is just using the third, hang on. It's just using the third column here in this. And so they're going to build another graphical function to add elevation in here. And the reason we're doing this is because that's really how we talk about the health of the lake. Nobody is sitting there measuring the volume of the lake directly. We infer the volume of the lake from the elevation and the topology. And so we just want them to be using the language that people are using while they're doing that. And so as we build this model together in class, we're really just adding this. And then we're also just spreading the other ins and other outs out into their more precise components. These don't really matter. They're not going to change as we go through it. But later, when I'm doing some troubleshooting with them, I like to have a few more things for them to consider as they do it, even though none of these are going to be the answer to something that that they're dealing with. So, so from this point on, we're just going to be talking, about elevation. And so at this point here, we use data sheet 2 to talk about information we need to provide for an interpretation of the elevations. So we pretty much are just giving them this very rough indication. When the lake's at 6380, severe dust storms are going to start at 6375, general ecosystem decline and so forth. And then if we get below about 6352, we'd expect somewhere in that area to see a general collapse of the ecosystem. And so This is really a rough estimate for them, but it does give them some way of interpreting the model, which I want them, to be able to do. I don't want this to just be about numbers. I want it to be about what does this mean for the lake. So then, still on Model 3, and we'll talk about this Model 4 part in a minute. But still on Model 3, the next thing we want to do is some validation of the model. Right? So we have a Model 3, and it gives us an answer, but how do we know whether this model is working right? Shape looks good, but what are the numbers? And so what we do with it is we go back to the values of the lake in 1941. We're operating in 1990 from the standpoint of where we stand in the class. So we go back and we change water in lake to 1941 levels. We run the model for 40 years and we ask ourselves whether in fact the model is correctly predicting where the lake ended up after 40 years. And so as we do that, we end up with this 6354, which itself is actually about 20 feet below the elevation we actually did observe there. And so most of this class is spent helping them to find their way to what is wrong. And this can be challenging because for many of the students, they don't really understand, the physics of what's going on with this. But as we move through this process and we look at all the different elements, we talk about, well, could this be the thing? Could that be the thing? And of course, where we always end up, because this is what it is with this idea of evaporation. And so, with the evaporation, we just have a fixed value. And as it turns out, the fixed value is the evaporation rate of fresh water. So saline water evaporates more slowly than fresh water. And we're not accounting for that. So we're not only using a too aggressive evaporation rate to start with, but as the lake level drops, that evaporation would continue to decline, and we're not getting the feedback of that over time. So this is the next thing that we're going to do, and this is going to be probably their most complex individual task of the model is solving that. So to do that, we step aside from Stellar for a moment, and we go back to a modeling system that they're already familiar with, a static modeling system, just to understand the concept of specific gravity, because we're going to use specific gravity to tie into the evaporation rate. And so we go back and we have them calculate the relationship, the specific gravity being just the actual mass of the lake divided by the mass of the same volume of fresh water. And so at our starting point in 1990, we have specific gravity of 1.076. Then we tie that in this Model 4 to an evaporation rate multiplier, which tells us that for different specific gravities, here's what the evaporation rate would be. So if we were at 1.1 as a specific gravity, then evaporation rate would be 92.6% that of fresh water. And so we want that to come into the model and to provide the feedback dynamically over time. And that's their assignment over the weekend. So they have them until the next Tuesday to do that. And you can see they have a lot of information here. They have the assignment spelled out. They have pretty much, if you look at this here, I'm kind of telling them everything they need to do it. But there it is. And then we talk a bit about this concept in there about thinking backwards, and I'll explain that concept in just a minute. And so they kind of have a bit of documentation here to kind of help them as they strike out, for it. So here's what I'm asking them to do in Stella. And this idea of thinking backwards, what I'm trying to express to them is to take where you are, what you know. So we're trying to find a new level of evaporation by a new evaporation rate that I'm just called actual evaporation rate here. Before, evaporation was just this freshwater evaporation rate times the surface area. And so now we need to modify this as the volumes of the lake change. So the idea of working backwards is I just basically ask them to take each element one at a time and ask, what do they need in order to find that? So if I want this actual evaporation rate, I know I need the freshwater rate, but I also need some kind of multiplier that will tell me how this changes. And in order to get the multiplier, I need specific gravity. And in order to find specific gravity, I need the actual mass of the lake and the mass of the equivalent volume of fresh water. And to know the mass of the lake, I need that mass of fresh water plus dissolved solids. For the mass of fresh water, I need to know, just as a constant, what is the mass rate for fresh water. So instead of asking to kind of visualize this all at once, I'm trying to ask them just to go back one at a time. And in each case, what you're doing is asking, do I need any other information to know this? So here, no, I don't. Here, yes, I do. So step back. What's the information I need? Here, do I need more information? Yes, I need these two pieces. All right, for this one, do I need more information? Yes, I need this and I need this. And for this, I need that. Do I need any more information for this? No, that's a constant. Do I need any more for that? No. And so that's how they know they're done. So that's the logic I'm hoping for them to step through, as they do that. And so as we go through this, they now have a working model. In this case, we validate the model based on the model that was actually used at the time. And so what we're looking for is an elevation after 100 years of about 6335. The model actually ends up coming in at about 6336. And so, excuse me. And so this is now a working model. And everything shifts here, because up to now, I've been asking them to document their models based on the technical things they're doing and what they added and why they did what they did. But from here on out, I'm going to be asking them to document their model based upon what the model tells us. And so as we look at this model, for example, I asked them to look down at the elevation values here, and not just to say we get to 6336, but what happens and when. So here we are, and we were standing in 1990, figuratively speaking. And so how long do we have before we reach, well, we're already at dust storms, but before we reach, say, ecosystem class? How long do we have before these different environmentally damaging events occur? How urgent is it that we do something with our policy here, or do we have a lot of time? We don't have a lot of time, as it turns out, but that's the kind of interpretation I'm asking them for here. So now we're ready, right? We have our tool, and we're kind of moving from modeling to policy analysis. And so first thing I asked them to do, actually, this is still modeling. I just asked them to exercise the model a little bit. Of course, this is a stable equilibrium that we're developing, but they don't really have a good feel for that kind of thing yet. So we talk about equilibrium and stability. And I just have them model, what happens if you come out and shock the system with some extra water? What happens if you shock the system water away? Does the system return to the equilibrium? And of course it does. But then moving into the policy, the first step is what I call with them setting the bounds. All right, what are the possibilities for the policy? And we really have two bounds here. One is we'll keep doing what we're doing, right, which is result down here in run 6 is is actually the same as that Model 4. But we also could say, well, no diversions at all, right? We'll just stop you from taking any water. And there's this one. But now we have some options in between, right? So as what happens if we take no diversion, if we allow 20,000 acre feet per year, 40,000 acre feet per year, 60,000, 80,000, and then the same 100 is already built into the model. And what I want them to do with it is to just get a sense of how this system works and what they can expect in this. And so, for example, we can see here that 60, 80, right? We're still declining. The system is not going to recover with these. We pretty much recover for around or so, and 40 is just kind of a bare recovery. You can see that the equilibrium here is not very high. So it's going to take somewhere, more like, maybe in the 20s and 30s is about all the water that's going to be able to come out of this system. And so I want them to have that feeling before we start into more specific policy questions. We also talk a little more about LA. They get some more context about what this water means to LA. At this time in 1990, this 100,000 acre feet is about 1/6 of LA's annual water usage. So this is a significant portion of the water they deal with. And finally, we start moving on to proposed solutions. These are solutions that were actually proposed in 1990. And so I want them to use the model to give me some sense of what those would mean. And so recall that the goal of the Water Resources Control Board was for the lake to recover to 6392. And one suggestion was a policy that had no diversions be allowed at all until the lake reached 6390, and that above that level, LA could take its customary 100,000 acre feet. So this isn't kind of an all or nothing policy, right? So we just model that in here. We come into diversions, and we just do an if-then statement, relating elevation to the target elevation, and whether or not there's zero or the historical diversion, takes place as diversions. And what you see here, and the students, before we actually run this model or build this variation of the model, kind of ask the students how reasonable it sounds. And for most of the students, they're kind of going, well, yeah, that sounds fair. But then we start to see some things that are kind of odd about this, right? This all or nothing means things are going to recover, and then it hits this critical point, and bam, they take out 100,000 acre feet, and so we have this big drop down here in elevation, and then it recovers and then drops. Now, these actually aren't terrible elevation levels from an ecological standpoint, and while it's not perhaps optimal to have sudden big hits, there is variation from year to year. So I'm less worried about the ecosystem here than I am about the feasibility of this for water diversions from Los Angeles. If you can imagine being Los Angeles thinking, well, this represents about 1/6 of the water we use, and what are we going to do? We're going to have zero water for, about 18 years. And then even once we are getting water, it's in this odd pattern, right? 2 years of zero, then we get 100,000 acre feet. 3 years of zero, then 100,000 acre feet, 3 years, right? And this pattern just continues along. And from the standpoint of people who need to be planning water use, maintaining aqueducts, doing maintenance and stuff, it just doesn't feel like a very suitable strategy to need the system running and then to leave it sitting there basically dry for 3 years and then run it and then leave it dry. So this probably doesn't really sound like a particularly great policy, not if you can find something better. And so we look at another policy that was suggested at that time, and this is called an adaptive diversions policy. And so it sets a buffer zone. And the idea of the buffer zone, I'm going to flip forward first and then come back. The idea of the buffer zone is that below 6380, there are no diversions. At 6382, you take 20,000 acre feet. 6384, you take 40,000, and so forth, until you get to 6390, where you take the customary 100,000 acre feet. This is intended to be interpolated. So, if you're at 6381, you get 10,000 and so forth, right? So you can fall anywhere on here. And so the idea of this is to try to achieve the goal in a smoother way, so that once Los Angeles starts getting water again, they can have some more consistent water, and eventually everything settles out into an equilibrium. The problem with this, of course, is that if you look at where this equilibrium is, right? So down here, we settle out to about 6383-ish. And there, LA is going to, as we kind of knew from the earlier runs, LA is going to end up about, a little over 36,000 acre feet. But this isn't going to really give us the kind of elevation that we can feel comfortable with ecologically, because of course, while our model, it looks like everything is nice and smooth, it's a deterministic model. We know that the actual variation in the world, is stochastic, and that, it's not going to be this, this smooth. And so probably looking at less than this, right? This is kind of one of the first places they really get to see the trade-off, where they're saying, look, if I want a higher equilibrium elevation, they're going to have a lower equilibrium diversion. And so that's really, in a way, the thing that we're trading off in a policy sense. So I want them to be thinking at this point, about the policy and how we do that. So, this leads to the last two assignments, right? The first is to model this, to bring this in, which is going to be yet another another graphical function. And then I want them to go in over the following weekend and develop their own policy, because this isn't quite there, but the idea is not bad. And so some students come in and, they're some of them just tweak the values of this adaptive diversions policy. But it's fun to watch the more creative students just taking off and just learning some of the really complex ideas, trying to find a way to please everybody. The only limitation they have, I give them no limitations on what they recommend. The only limitation they have is they have to be able to model it. So I do insist that they have a model that shows their policy and what their expectation is for how that would go. So, basically, that's the assignment, right? That's the end of the assignment. And so, to bring it full circle, right, to kind of help them to feel a sense of completion here, then that this policy actually had some meaning when it really happened. The first thing I do, two things. The first thing I do is we go back and we look at the policy that actually was adopted. And this was adopted in 1994. And this is a policy that still exists today. So the goal was to rebuild the lake toward an equilibrium of 6392. The city's allowed no diversions until the lake reaches 6377. Between 6377 and 6380, they can take 4,500 acre feet. And when the lake is between 6380 and 6391, they can take 16,000 acre feet. And if the elevation exceeds 6391, then the city may take, and this is like a real kicker, that you can just see the political compromise here, all water in excess of the minimum ecological fish flow of 30.8. So that's going to be, on average, about 120,000. So even more than they were taking before. And, if we've been watching the previous models that have these hard lines, we know what's going to happen, right? We're going to come up and then knock it down and up and knock it down and so forth. And they're going to go along with their 16,000 acre feet. And every several years, they're going to get a big bump, and then they'll be back at their 16,000 acre feet, and so forth. At least, if the model runs like that. Of course, one thing I want the students to note is with this model, you can never achieve your goal, right? If your goal was 6,392 feet and you start knocking the water back at 6,391, then having stated that goal, you've just developed a policy that cannot reach that goal. And the second thing we do to kind of wrap this up is we go out to the Mona Lake Committee website today, right? And we look at how that policy has turned out 40 years later. So here we are, November 1st, just a few weeks ago, right? 6382. Ouch. You know, this has not been a very successful policy here. And just in case, you know, you kind of wonder, well, maybe it's just, you know, a dry time right now. Here's the highest it's ever been in the last 40 years. All right, 6385 is the best we've gotten, even in the best of years. So I do want them to understand that you know, I mean, here we are, 40 years of this policy in place, and we're not actually achieving what we wanted to. The other thing I want them to think about here is kind of the last steps in modeling, because this isn't what we thought, what our model thought would happen, right? Here's our model. It's suggesting we're going to be bouncing up there over 6388. Right? We'd be bouncing around, but we'd kind of be up there, and we're not. All right. So this kind of gives me an opportunity to talk about kind of the last stages of modeling, which is observing your models, observing the world, observing how your predictions go are doing, and going back and revisiting and revising your models as an ongoing process. Something which as far as I'm unaware of whether anyone has continued to do this or not. There's very little information about that. So that's pretty much it. A few variations that we discussed, just so that you know that we do it. We look at a couple of stochastic versions of the models. You know, it gives me a chance to talk about the strengths and weaknesses of deterministic models. And there was at the time an ecological model based on the brine shrimp. And that is a relatively much more complex model than the one that we build here. But we do take a look at that model as a module of the overall model, and we integrate it with this one, and we look at what that tells us about the policy. And it helps me to kind of make the point that, you know, more complex isn't necessarily more useful, because that dramatically more complex model pretty much gives us the same policy advice as this more parsimonious model. And so that's about it. As I wrap up, I just want to put maybe this Mona Lake project within our broader curriculum. We use Stella in multiple courses across the environmental curriculum. In our introductory course, students build a few conceptual models focusing on structure and feedback, but they don't assign numerical values. In more advanced courses like this, we build fully functional models. In this particular course, we begin with Excel-based models and either MapleFlow or R models, depending on the instructor. And then these tools help students to grasp static relationships and basic system logic. But then we introduce Stella as their first exposure to dynamical modeling, where time, feedback, and accumulation come into play. And so toward the end of the course, then, I also ask students to go back and use all of these modeling systems to build an issue in all three platforms: Excel, MapleFlow, in my case, and Stella. And this comparative exercise really helps them, I think, to see the strengths and the limitations of each tool, right? And perhaps more importantly, I think it reveals when a system's behavior is truly dynamic, and they start to recognize that static models really can't capture feedback loops or time-dependent processes. And that's an insight, you know, I want them to have, whether they ultimately end up to be a modeler or a policy person or you know, whatever role they take on in the environment. But that's about what I have. I see I'm running just a little behind here. So let me just invite, if anyone has some specific questions, you are welcome to email me. And but you know, we'll have time for a few questions here, whatever I've left us. Hillary.
Great. Thank you so much, Rob. We don't have any questions yet, so I will give people a little bit. But while we are waiting, I do have a question. During the whole process, did you find there was one step that was more difficult for students to grasp than other steps?
Yes, it is when we get adding the specific gravity thing to it. Um, Honestly, most of our students have never heard of the concept of specific gravity, so they're they're being introduced to a new physical concept. They're having to figure that out. They're learn the math of it, and then because this is their first real in-depth Stella experience, they're used to putting math equations in an order in a static model, but they're still not really very comfortable yet in expressing this in terms of stocks, flows, and in this case, a whole series of converters. And so that is the step they find challenging. And beyond that, I've done this for quite a few years now. It's gotten smoother and smoother over time as I've kind of learned what works for them. And I think it's pretty smooth at this point. I don't think anyone struggles too much.
Great. Here's a question. How do you know that the target elevation is best for the surrounding ecosystem?
I just take the word of the people who have said that this is the target, right? In other words, I didn't set the target, and as a policy analyst, I wouldn't be setting the target necessarily, right? The Water Resources Control Board, through a political process, decided that 6392 would be that target. Now, I am playing a little fast and loose with the timeline here with the students. They didn't actually set that until 1994, and the modeling was being done in 1990. But I take some of those decisions and I feed it kind of back in time a little bit so the students have a little more structure in what they're doing. I feel like that's easier for the students than having them not have a specific target in mind.
So this person says, thanks, Rob, for the fantastic presentation. Any thoughts about how you would integrate general AI as a tool to this fabulous exercise?
Oh goodness, that is the joy of retiring at the end of last year. I only had 2 years where I was having to deal with AI in the classes. So no, to be honest, I haven't thought about how I would put that in, but I absolutely would if I were continuing to teach. My view of AI is not the doom and gloom sort of view. I think it's a powerful tool. I think students can make use of it in many ways, and I would be looking for ways to help the students to see AI as a tool, perhaps helping them to work on a problem like this.
Do you see bigger value from quantitative modeling compared to qualitative conceptual modeling?
No, we do both in our various classes. I don't think the quantitative is necessarily inherently more valuable so much as it's one of many tools that we should use. And I think there are some kinds of things like this that are very well suited for quantitative modeling, and yet there are many other kinds of things that I think are much better dealt with qualitative modeling. And we see that in the environmental realm, right? We see that with the the way people view environmental issues, with the political pushback and the way we communicate about environmental things. Those aren't things that are conducive to quantitative modeling, but they're absolutely critical for dealing with environmental issues.
Does LA receive any sort of legal ramifications for the lake not being fully recovered?
I don't know. Yeah, that's a great question. I only know what I read out on the Mono Lake Committee's website, and basically the status that they say they're at is they have been pushing for several years now to have a new review of the rules, and they would like to redo the modeling, and they would like to reconsider the rules because they still believe the 6392 to be a valuable goal. And so but they've been unsuccessful in getting in getting the state to agree, to do that. There's actually some really interesting stuff on there too. They talk in some casual detail. They don't go into great depth, but they go into enough to give you a sense that they felt there were some problems with the models. They recognize that climate change has changed the climate. And so that their decisions were based upon average annual rainfall that simply doesn't exist anymore. And so as you actually go through that, you see all the elements that you would look at. If you looked at our model and you said, wow, what's wrong with that model? They do a really nice job of enumerating, those different things.
Great. How do you verify the relationship between EV and specific gravity of the lake water?
So how do I verify it? I don't. I take that as given. And Andrew provides those values, and I just presume that he did a good job in coming up with that. I am not a physicist. I'm not a physical scientist. I'm an economist. So when we get into that realm, I let people with more experience with those things just tell me what the relationships are.
Great. Those are all the questions we have right now. Thank you so much for this presentation. We really appreciate it. If anyone is interested in other presentations, please email us. We would love to have your insight on where we would be moving next into this series. Well, we will see you for the next webinar in a couple of months.